so the topic that I'm going to present is called Reversing and Deciphering Cyber Espionage Malware Communications. So pretty catchy title. Okay, so as the name says, the focus would be on the cyber espionage malware. So I'll be reverse engineering. We'll look at the communications of a malware that was used in an actual APT attack, which targeted the Taiwan and Japanese government organizations. So in this case, the malware communicates to the command and control server, but the traffic is encrypted. So in this session, I'll talk about how to reverse engineer the sample, identify the encryption algorithm, identify the encryption key, and then how to decrypt the communication. So this is just to make you understand the modus operandi used by the attackers. So hopefully at the end of the session, you get an idea of the techniques that the attackers use. So before I move on, let me introduce myself. My name is Monnappa. I work with Cisco CSER team. So I'm part of a team called Threat Intelligence Team, where we focus on investigation of APT attacks within Cisco, and we also do external research and intelligence. So where we interact with groups that work on APT attacks, and we share indicators, we share the samples, we try to understand the modus operandi of the attackers, the motives, the target that they use, and the sectors that they target, and so on. Okay. And my fields of interest are reverse engineering, malware analysis, and memory forensics, and that's where you can get in touch with me. So this is the content for today. So the first I'm going to talk about a malware called Etumbot, which is a malware, like I said, which is used in an APT attack. So then I'll talk about the espionage campaign, give you an overview of the attack, and this would be like 5 minutes. And the rest 35 minutes, I'll be focusing on the video demos, where first I'll show you the sandbox analysis of this malware, and show you why sandbox analysis is not always, cannot always give you all the answers. So then we'll move on to the topic where I'll show you how to reverse engineer the sample to understand this encryption algorithm. And then in third demo, I'll show you, once you understand the encryption algorithm, how to decrypt the communications. Okay, so let's get started. So this will be a brief on Etumbot. Etumbot is a malware used in, like I said, cyber espionage attacks. So it's associated with the Chinese espionage group, which we track as, there are different names for the Chinese espionage group. So many security vendors have their own tracking mechanism. So it's numbered panda, APT12, calping. So these are all the same names for the actor group. So it started out, the targeted attack started out with a spear phishing email, which I'll go to the details in some time. And it targeted the Taiwan and the Japanese government organizations. So once executed, the malware would open a decoy document, which looked like it is some legitimate document, which is related to the Taiwan and the Japanese government. Okay, so that the users don't suspect that it's a malware. So these are different names. Explore, specific, riptide are different names for the malware. So this is the campaign. If you're not able to see the screen. So it started out with a spear phishing email, so which had a 7-zip file in it. So once someone extracted the 7-zip file and executed a sample, it was like .scr file or .exe file. So executed the dropper, it would drop an additional component. So it would drop another file, which is winlog.date.exe, which is your Etumbot backdoor. So what this backdoor would do is, it would contact the command and control server here. It will get some data, so it gets the encoded data from the command and control server, decodes it, and then extracts the RC4 key. And then what it does is it collects the system information on the system, and then uses the RC4 key that it extracted from the command and control server to encrypt the traffic, encrypt the collected system information, and send it to the attacker on the command and control server. So we'll go deep into this, so that's what I'm going to focus now. So first we'll start, so you'll get an idea of the actual attack. Okay, so first we'll look at the video demo is, so the first we'll look at the analysis of this Etumbot dropper to see what it does. Okay, so let me bring up the video demo here. So this is the sample, this is the malware sample. I just renamed it as 5340.exe. So what I'm going to do now is, I'm running this malware sample, that is 5340.exe, in a sandbox, which is a script which I wrote. I'm running it for 60 seconds. So once I play the video, you will see a lot of things happening on the screen. So what the sandbox is doing, it's doing the static analysis, and then it will pop up the VM, it will transfer the malware to the VM and does the dynamic analysis. While executing, it will monitor its activities and reports it back. So it also does memory forensics. So you don't have to worry about what the tool does, but let's focus on the malware. So what I'm doing is I'm running the sample for 60 seconds. I'm playing the video. As you can see here, it's doing static analysis. It is determining the file type, the MD5 hash, and then it would search the MD5 hash on the virus total. As you can see here, and it's running some monitoring tools. And as you can see here, it started executing the sample for 60 seconds. So before that, it ran the monitoring tools. It is executing the sample for 50 seconds. And you see here the VM is popped up, and inside the VM it is executing the sample. Okay, so now once it executed the sample, it is stopping all the monitoring tools, and then it will suspend the VM, the virtual machine, and does memory analysis and stores the results in this directory here. As you can see here, the final report, the packet capture that was captured while executing the malware sample is stored in this directory. So let's look at the reports and see what the malware does. So this is the report file, it is sandbox report.txt. Okay, so let me open that, show you what the malware does. As you can see, these are the static analysis results from the sandbox. You can see that it determined the file type, which is executable file. You know the architecture it's targeting is Windows. And this is the MD5 hash. And these are the virus total results. As you can see, some AV vendors detect this sample as malware. Okay, some don't. And this is the dynamic analysis result. So this is the results got after executing the sample in this in the virtualized environment. So let's see what it does. As you can see here, the process got created. The sample that we executed, successfully executed, that's 5340.exe. And after executed, you see that here, you see a file right here, the 5340.exe writes a file in this application data directory, and the name of the file that it drops is winlog.date.exe. And also, once it drops that file winlog.date.exe, it created that process out of winlog.date.exe. So basically what the malware is doing is dropping a component and executing that drop component. So it creates this is the backdoor that we'll be looking at. Okay, so far we know that so when executed, it drops a file, it executes that file. Then this is the DNS summary. So it contacts this command and control server here, which is www.publiclog.com. So this is the command and control server. It is doing a DNS query. It is trying to resolve that domain. So once resolved, you'll see that it makes an HTTP request. It makes an HTTP request. You'll see that there are two sets of patterns here. So one is /home/index.asp, and there is another pattern which is /image/ some random name.jpg. Okay, so it looks like it is a normal request. When you're doing a monitoring, it looks like nothing. There is nothing wrong here. It's just a normal request. It looks like the first communication looks normal. The second one looks like it's a download. It's downloading an image file. Okay, so nothing abnormal. So we'll look at that. And also, the malware also adds itself into the run registry key here. It adds a value with a value name as update, and this is the path that adds into the registry key. So that is the path to the dropped file, the file that it dropped onto the disk. So this is the path to the file that it added to the registry key. So the reason why it adds that is so that for persistence, so that whenever the system reboots, this executable would get executed and the malware would get executed. So that's the reason the malware normally adds get entry into the run registry key so that they can survive the reboot. Okay. So far, just to summarize, this is what it did. Once executed, the dropper, that is 5340.exe, it drops a file which is winlogdate.exe, and then it added itself into the registry key after dropping it so that it can survive the reboot, and then it made a DNS query to the command and control server, okay, and then it had like two patterns. It communicated with two set of patterns. You just remember the patterns, I'll come back to this. So one has this /home /something and then /image random name.jpg. Okay, so now what we'll do is let's look at the packet capture. See, I told you that the sandbox also captures the packet while the malware was executing. In this case, you see that the same thing, it made a DNS query to that command and control server domain. And then you see that once, which resolved to 192.168.1.3, and you see that once it resolved, it made a connection on port 80. Okay? So this is the same thing that we saw in the HTTP request. So this is the first set of communication. So this is the GET request that we saw /home /something. Also notice the referrer header, which is google.com, which is a hard-coded header to make it look like it is coming from Google. So while you are doing your monitoring, this is what you'll see. Or when you run it in a sandbox, this is what you'll see. Everything looks normal. There's nothing abnormal here. Another thing you see, it's making a connection to this command and control server. And what it is doing is, here, it is receiving an encoded traffic. So which looks like a base64 encoding. Okay, but if you look at the last two characters here, it's not equal to, it is --, so it is a custom base64 encoding. So which means you'll not be able to decode it using your standard base64 encoding, so you'll have to do a little bit of modification to decode it. So now we know that the first communication, which is a /home something, it gets some traffic from the command and control server, and we'll see what it does with it. And the second set of communication here, let's see. Okay, this is the second set of communication, where it is trying to, what looks like it is trying to download an image file, like I said, the random name.jpg. Okay, so this is the second set of communication. Okay, so this was the sandbox analysis, just to show you that the two set of communications. Once executed, the malware drops a file, adds itself into the registry key, communicates on the network. But once the first communication is taking an encode, it's taking the base64, custom base64 encoded data, does something with it, and there's a second communication which looks like it's a request to an image file. So, but from an incident response perspective, we want to know what exactly is this communication, how the malware is using this data that it received from the command and control server, or what is that request to an image file? Is it really a request to an image file, or is it something else? So in order to understand that, we need to do the reverse engineering. So that's the second video demo about. So now we know from the sandbox analysis that there are two sets of communication. Now the idea of reversing is to understand what these communications are, or how the malware is using the encoded data from the command and control server. So in order to do that, what I do is I create a fake file, which is fake HTML I call it fake file.html, and I downloaded the content that it received from the command and control server, the actual content, and then copied it in the file. And what I'll do is, I'll be running a tool called inetsim, which simulates all the services. It will simulate the DNS, it will simulate the HTTP server, SMTP server, and all other services. The idea is the two things. So one, not to allow the malware to connect to the actual command and control server. But when the malware is trying to connect to the command and control server, the inetsim will give a fake response saying that www.publicloud.com is at this IP address, which is the IP address which I control. So what I'm going to do, in the same host, I'm running the fake HTTP server and giving this fake HTML content, so that when the malware is requesting for that /home /something, it will get this data from my local machine. So that's the idea. So the idea is, once it takes this, what does the malware? What will the malware do with it? That's the idea. That's the idea. Okay. So once I created this file, that's myfake.html. What I'm doing is I'm starting running this inet sim tool, which simulates all the services, including the DNS, HTTP, all other services. Okay, so as you can see, it's simulating all the services, so that when I'm debugging the malware, all the traffic would go through this. And let's say if it is querying publiclog.com, it would say that publiclog.com is at this IP address. Then it will perform its next activity, that is communicating to the requesting that the encoded content. So then I can give the content back to the malware. Okay, and also, what I'm doing is I'm running Wireshark on this machine, so that I'm capturing the traffic while I am reverse engineering the malware, or while I'm debugging the malware, so that I understand how the malware is communicating on a network. Okay. And then what I do is I go into the Windows machine where I'll be debugging the malware. Okay. So for the sake of demo, what I've done is I've set multiple breakpoints at places which are interesting. So when I run, it will hit the breakpoint, okay, and then I'll be explaining stuff. So first, the first breakpoint is here. As you can see here. So in case if you don't understand assembly, it's fine, but I'll try to make it simple. So I won't go into assembly details, but try to make it simple. So don't worry about the assembly in case you don't understand assembly. So the first function is this function, call to a function which I renamed it as first C2 communication, because after analysis I know what is the purpose of this function. Okay. So let me show you this. Why this function is of interest is because if I want to understand the network traffic, I need to find the function which calls the network related API calls, right? So just showing the call graph here. Oops, I think that's not good here. So but let me read out. So all the entries in the ping. It says HTTP open request, HTTP send request, HTTP end request, internet connect, internet open. So this function is going to call, at some point, all these API functions which are network related functions, which means I know that I've landed on a function which has some kind of network activity. Okay. So now I get into this function because I know that this is a function of interest. Again, I land up on a few other functions. Again, I've renamed it based on that, and then, okay. So then, we land up on this function, which is anything that is marked in pink is the Windows API call. Okay. So you see that while debugging the malware, I land up on this function, which is internet connected. So if you look up MSDN or the Microsoft documentation, you will see that this is an API call that is responsible for opening a HTTP session with a site. Okay. So in order to know which site it opens a session, that is in the second parameter that is on the stack here. So which I'll show you. As you can see here, I'm looking at the second parameter, which is 40B95A, which is this address here. And you see that the site it's going to connect is www.publiclog.com, which we saw in the sandbox. But you see that it uses this API call to establish a connection to this particular site. Now I know that the malware is going to open a session with this particular site, publiclog.com. So what next? So next, let's run the sample and see what is the next breakpoint. Here, the next breakpoint I hit is this HTTP open request, which is another API call. This API call tells you what is the request parameter that it uses, whether it will use a get parameter or a post, and also it will tell you what it's going to request. Okay, so that is in the, I think, second parameter. If you look at it. As you can see here, the second parameter on the stack tells you what it's going to do. So it's a get request. I know that it's going to do a get request. So it's going to establish a connection with that particular site, www.publiclog.com, and it's going to make a get request. And the next thing is, the third parameter will tell you what is going to request. As you can see here, this is what it's going to request. So this we saw in the sandbox, right? So now I know it's going to connect to the command and control server. It's going to use get request. This is what it's going to request. Okay, so let's land up on the next API. So the next API that it calls is HTTP send request. So this is the API call that is used to send the traffic onto the network. So far, the traffic is still not on the network. Okay, so only when I execute this API, you will see the traffic going on the network. Okay, so it's like a printf statement which will print the content onto the screen. The same way, after this API call, it would send the traffic onto the network. Okay. I've not executed the sample yet, so I'm just showing you the packet capture that there is no communication to public log before executing that function, the API. Okay. Okay, after I execute, you see that there is a DNS request to that domain, the publiclol.com, and after it resolved to this IP address, 172. Which is my Linux IP address, and it made this HTTP connection here, and you see this request here, get home something that we saw while debugging. So let me show you the traffic pattern. As you can see, this was the pattern. Again, you don't see the second pattern yet because we have not reached the code of second pattern where it will request the image file. We are still in the first pattern. Okay, so as you can see, it is requesting this home, and also you see what's important is we are giving this data that we collected from the command and control server to the malware. Right, so this is the data. This is the same data that I downloaded from the actual command and control server, so which I'm giving it to the malware. So now this is where our actual analysis starts to see what it does with this data. Okay. So this is the API call. The internet read file, like how HTTP send request was the API call to send the traffic onto the network. This is the API call that is used to receive the traffic from the network. So which means after I execute, the data that it received, the encoded data, the base64 encoded data will be stored in a buffer, which I'll show you. The data that we gave. So this is where now it's all null bytes before executing that API function. This is where once I execute that API function, you will see that it will download the content that it got from the command and control server and store it here. Okay, so let's see. So after I run this, you see that it got the malware got the encoded data, which normally this is how it gets the data from the command and control server, and now what it does with this data. So that's an interesting part. Okay. So once it gets this data, first thing it does is, so I've analyzed the function and I've renamed it as custom base64 decode. So I know that it gets the data. The first step is the malware is going to do a decode of this data. So the first parameter to this function is what to decode, that is this traffic here. And then the second, or I think third parameter will tell you where the content, that decoded content. So that's the first parameter, that's the content to decode, which is the content from the command and control server. And the third parameter here is where it will store the decoded traffic after I execute that function. Okay, so execute, okay. So this is the traffic, this is the decoded traffic. Now, let me tell you what it does with this traffic. So what it does is basically starting from the 8th offset here. So now it received the content from the command and control server. It used the custom base64 decoding. It decoded the content. Then what the malware does is starting from the 8th offset, that is this here, 65, 36, whatever, till the null byte that is here. Okay. So which is same as E65 WP24N5. It will extract this string, and it will use this as the RC4 key, so which we'll see in some time. So basically what the malware did was, in the first pattern, it got the command and control server data from custom base64 encode data from the command and control server. It decoded the content. It starts, after decoding, starting from the 8th offset till the null byte, it's going to extract whatever that string is, and it is going to use that as the RC4 key. Okay, so So once extracting, it will store in this memory location. So which I'll show you after extracting from the 8th offset. So it's going to, as you can see here, it extracted the offset from the 8th, that is the E6 WD24N5, from the 8th offset and stores it here. And then this is the RC4 key that it uses. I'll come to how it uses this key in some time. So now that was the first communication. Now we were able to understand how the malware is going to use the encoded data from the command and control server. So first it makes a communication to the command and control server, takes the encoded data, which is custom base 64 encoded, decodes it, takes the 8th offset till the null byte, extracts it and keeps it. So then comes the second communication, which was the image the image slash something. So again, the reason why this function was interest was because again, this was another function which had references to other network related API calls. Because if I want to inspect the network traffic or decrypt the network traffic, I need to identify the API calls which calls the network related API. So now just show you the call graph again. I'm showing you the call graph showing that it has references to all the it's not visible, but it has references to the network related API calls. Okay, so I'll go into this function. Okay. So what it does is, I've renamed the function here. So after analyzing, because I know that it's an RC4 encryption, after analyzing I know that it's an RC4 encryption. So once it took the data from the command and control server, got the RC4 key, next it does the second communication, and what it does is, it calls a function which is an RC4 encryption function. The first parameter to this function is, of course, what to encrypt. And then the key, that is the key that it extracted from the command and control server, and then it's going to encrypt the data. So now the question is, what is it going to encrypt? Okay. So this is the first communication of the malware. Okay, so as you can see, the first parameter to this function is this, which is this here. So, which is my host name, pipe, administrator is my username, and then 172.16.49.128 here is my IP address, and it also says whether there is a proxy in the system or not. So this will be the first communication to the command and control server. So this is what it's going to encrypt, okay? Which is the system information that it collected on the infected machine. So just to show you that these values, okay, as you can see here, this is my host name, which is the one which it collected here, Mona hyphen whatever. And then administrator is my username, which is this. And my IP address where I'm running the malware is 172.16.49.128 here. And it also reporting to the attack, it's going to report to the attacker that it's no proxy. Okay, so this is what it's encrypting. Okay. And once it encrypts, it stores it in the third parameter here. Okay, this is after executing that function. This is the encrypted traffic. And this encrypted traffic is nothing but the system information that was collected from my machine. So as you can see, now it doesn't make any sense here. Okay, then what it does is, then it calls a custom base64 encode function. So it receives the encoded traffic from the command control server, gets the key, collects the system information, uses the RC4 key to encrypt the traffic. That encrypted traffic is further encoded using the base64 encoding algorithm. Okay. So this is the encoded traffic. So you probably can recognize this traffic if you carefully observe the sandbox analysis. Okay, so this is the encoded traffic. Now this is RC4 encrypted and then base64 encoded. Now this is the base64 encoded data. Let's see what it does with this next. And also you see there is string concatenate function, which means it's going to concatenate the string with something. So what is it going to concatenate with? Is this. It's going to concatenate with image. So it's going to concatenate with slash image. Okay, so slash image slash and then that encoded data. Here is the input data. So the final after concatenation. After concatenation, this is what it would look like. Slash image slash encoded data, which is again system information in the encoded RC4 encrypted and then J64 encoded. And then it calls another string concatenate operation and concatenates with the string.jpg. Now if you remember, it is slash image slash that encoded data dot jpg. Okay. So basically malware built that string now. Okay. Then let's see what the malware does. Again, so then once it concatenates the string, once it collects the system information on the infected machine, concatenates with the image and the .jpg, it again uses the network-related API calls to communicate on the network. So it calls Internet Connect. Again, like I said, this is the API call which tells you which site it is going to connect to. So let's see. In this case, again, it would connect to the same site where it was communicating first. The attackers can change this site, but it's again communicating to the same command and control server domain. And then it calls HTTP open request. Like I said, you get information as to what method it's going to use, whether it's a get or post, and also what it's going to query. So in this case, you see that it is get request. It is going to make a get request. It is going to request this slash image slash that encoded data.jpg. So it looks. So now you know what, this is not an image, it's not a download to an image file. Basically it is going to pass the your system information to the attacker, but while you're monitoring it looks like it's someone is downloading an image file. So it's not really an image file, the attacker sitting at the other end. Okay, so then it hits this API call where it will send the traffic onto the network. So after it builds the string, after I run this function, you'll see that the second communication going out on the network. As you can see here, this is the second set of communication that went out on the network. As you can see here, this is what it concatenated, and you now know that what this encoded data is. It's a system information collected, it's RC4 encrypted, it's custom J64 encoded. Now the attacker sitting at the other end knows, because he's the one who wrote the malware, he knows that he has to decrypt this part to get the system information. So this is the first communication. All subsequent communications are encrypted this way using the same encryption algorithm and the key, and sent to the attacker using the same communication pattern. So the attacker sitting at the other end would just probably to just make it look like he's serving an image file, he might serve an image file. It really doesn't matter for him. For him, what matters is what's this part here. This is the encrypted system information that is going out of your network. Okay. So this was the second demo. As you can see, sandbox was, when you run it in a sandbox, what you see was just the encrypted traffic. It does not give you, it does not decrypt the communication and so on. But from, like I said, from an investigations perspective, you want to know what is going out of your network. So in that case, you want to decrypt the communication, understand the encryption algorithm, understand the encryption key. So now once you have it, because the attackers, the APT actors normally use the same set of malwares. So once you have once you know the communication pattern and the key, what you can do is you can write decryptors and keep it ready so that when you have other infections, you can just take the decryptor, decrypt the communication, and then you don't have to reverse engineer the malware again and again. Okay, so that's a third demo. That's a quick demo, so that won't take much time. So now we know how the encryption algorithm works and the encryption key. So what I'm going to do is, I'm going to take the first traffic, because to get the encryption key, I need the command and control server traffic, the traffic from the command and control server. So the first script, what it does is, it takes the traffic from the command and control server and decodes it and extracts the RC4 key. So like it decodes using the custom base64 encoding the same way the malware decodes, and then extracts the RC4 key from the 8th offset till the null byte and displays it on the screen. So let me show you that. So this is the script which I wrote. So this attack happened in 2014. So this is the script. What the script is doing is, this is the main function. It's just getting the key. As you can see, it is reading, it is decoding the content, which is the custom base64 decode. It's getting the data from the 8th offset till the null byte, and it's going to print the RC4 key onto the screen. So let me run it. I call it the getKey.py. I take the traffic from the command and control server. This is the script, Python getPy, and then it takes the encoded content as a parameter. As you can see here, it took the encoded content as a parameter, and it output saying that extracted RC4 key is this. So which is the same thing that we saw while we reverse engineered the sample. So which means we are correctly extracting the RC4 key. Okay, so now once you have the RC4 key, you know that you can now decrypt the communication, which looks like a download to an image file, right? So that's the second script. So what the second script does is, it's going to take this part, that is the part after image slash and the part before the .jpg, because we know now this is the encrypted system information that is going out, and we also have the key. So this is the second script. Again, I've just hard-coded the key here, so you can actually, you need not hard-code it. So in this case, I've hard-coded the key. So what the script takes is the second encoded and encrypted content and decrypts the content using the key that it extracted from the command and control server, and shows you what went out of your network. As you can see, I'm taking that part here, the encoded traffic. This is the output from the sandbox. So I run it, and you see that the decrypted output is this. My host name is the host name of the sandbox machine where I ran the sample. Administrator is the username. This is where the IP address of the sandbox, and doesn't have any proxy. So this is the first set of communication. That way you have a packet capture solution in your organization, and you see this traffic, you know this malware, once you identify the encryption algorithm and the key, you can decrypt all the subsequent traffic and see what exactly is going out of your network. So the same way the attacker decrypts at the attacker end. Okay, so I think with the video demo, I think with this, I'm glad everything worked. So also the screenshots, just a screenshot from the analysis. So with this I complete. So just to mention that in this case the attackers did not store the encryption key in the binary. So it was in the command and control server. So they can change the encryption key by giving different content every time. So then the malware can, if the content is changed, let's say it was encoded with some other content, starting from 8th offset, the key would be something different. Then the malware would use that key to communicate, to encrypt your system information. Okay, that's an interesting tactic, because most of the malwares that we see is in the APT attack they normally have the key in the binary. In this case, if the command and control server goes down, you won't know the actual key, right? So that's another thing. Okay, so if you have any questions, I think with this, yeah.
You say how you figure out the encryption algorithm?
Yeah, so again, reverse engineer, go to that function, understand how it works. Let's say RC4 function, understand how RC4 works. So you will see, yeah. So I've not shown that, but I just, after I analyze, I rename the function, so that next time, otherwise you have function names like sub underscore something, which won't make sense. Right, so if you open IDAPRO, the function names like sub underscore the address of the function. But once you already analyze, it's always good to rename your function so that you know what function you're talking about next time when you analyze it. So that's why I rename the function to RC4 encryption.
Any other questions? have one more question.
Yeah.
You said that there were basically two target countries or governments for this attack.
Yeah.
Do you know that it's not more widespread, and how similar was it?
They use the same malware based on, so basically like from the threat intel group, one of the things that we do is, so who the actors are. So that is based on the modus operandi, the motive, the command and control server that was used before. So we already have intelligence on around 40 Chinese APT actors. So we know from the command and control server that was used, we know who it was associated with previously, and they previously targeted Taiwan and Japanese. So we have an idea that, okay, this is from the same actor group based on their modus operandi, the motive, the target that they choose, and the infrastructure they use. So that's how we were able to determine that it's from the espionage group, but nowhere else it was targeted. So it was targeted towards that. So once they found out, I think they might change the tactics. Yeah. So mostly.
Let's hope not.
Yeah, hope not. Yeah.
So, still no questions?
Okay.
Thank you very much.
Thank you.